Anshu? Okay. When A and B, they commute, it means that they can be measured. Please note, and I am emphasizing it, that when two operators, they commute, it means you can measure both of them with same level of accuracy simultaneously. When simultaneously mean at the same time you are measuring two quantities A and B, and it means that there is no uncertainty in their measurement. They are very correct value, they are accurate value, there is no fluctuation in them, and they are constant. Okay, so no problem with that. However, when A and B do not commute and answer is non-zero, then it means that there is uncertainty in them. There is uncertainty in them, and look here, Lx and Ly, they do not commute. Answer is that it means that if you are measuring the two component x and y component of angular momentum of a particle, then they cannot be measured with the same level of accuracy. Okay, there is uncertainty in there, and when there is uncertainty, they should obey the uncertainty product, that is delta Lx into delta Ly. It is equal to something. Okay, it is equal to some h bar over 2 pi or something like that. Similarly, delta Ly, delta Lz is equal to that, and this is here as well. Now, what is the reason behind? Okay, they do not commute. The reason behind that angular momentum L, vector L, the angular momentum, it is a vector L, and it is such a physical quantity that during the course of motion, it is fluctuating. It is fluctuating. However, when you make a square of this, if you make a square of this, then you will find that L square Lx is equal to 0, L square Ly is equal to 0, L square Lz is equal to 0. What a strange thing. You have L is equal to Lxi plus Lyj plus Lzk. 3 components, Lx and Ly. You take one of them and you take other of them, they do not commute. You take this and that, they do not commute. You take this and that, they do not commute. It means that there is uncertainty in their measurement, and hence there is uncertainty in measurement of L, and hence L is not a good quantum number. L does not represent a good quantum number. However, if you make a square of this, square of L, which is L dot L, because dot product of one vector and another vector. So what is L square? L square is L dot L. Okay? It is square of this, and L square is given by this expression, and you take one of them. Like here you took one, and you take one component of x, L square and Lx, then they commute. Very strange. Okay, Lx with Ly does not commute, but Lx commute with L square. Ly commute with its square. Lz commute with square of L, and it means if you are making measurement on L square and any one of the component of angular momentum, then they commute. What does it mean? It means you can measure L square and any one of the component of angular momentum simultaneously with accuracy. There is no uncertainty in their measurement, and hence L square, the quantum number which corresponds to L square, it is a good quantum number. Okay, so what we say in quantum mechanics, the angular momentum L is not a good physical quantity, but its square is a good physical quantity. Okay, its square is a good physical quantity. There is no uncertainty in measurement of L square Lx, L square Ly, L square Lz, lekin there is a uncertainty in Lx, Ly and Lz, so it means there is uncertainty there, but it will not show any uncertainty product. It will not show delta L square, delta Lx is equal to h bar over 2 pi, something like that. Okay, so it means that if you have this expression to represent L, then there are uncertainties in there. Okay. One thing more. Look at all these mathematical things and think of physics. The short outcome of physics out of it is that 3 components of angular momentum are there. They do not commute with each other with the same level of accuracy. However, square of L square commutes with every one of its component, and hence it does not have any uncertainty product, whereas its 3 components among themselves, they have uncertainty product. Okay, so that is one thing. फिर इसके बाद we are going to define 2 new operators, and new operators are that is when quantum mechanics progressed, when need arises, then they always have new operators. I am going to write an operator L plus, which is defined as L plus Lx plus ILy, and L minus is defined as Lx minus ILy. It means take Lx, the x component of angular momentum, add it with y component but multiplied with I square is minus 1. Similarly, L minus is Lx minus ILy, that is, you subtract Ly by multiplying it with the I from Lx. Okay, this is how they are defined. L plus and L minus are defined like that. Now, if you say, okay, what are the corresponding expression in spherical polar coordinate, then in spherical polar coordinate, the corresponding expression are the following. It is h bar e raised per I phi delta over delta theta plus I cotangent theta delta over delta phi, and this is equal to minus h bar e raised per I phi minus I phi delta over delta theta minus I cotangent theta delta over delta phi. These are in spherical polar coordinates, because I told you, you can go back and forth from rectangular coordinate to spherical polar and spherical polar to rectangular. Now, what are they? They are known as in quantum mechanics is step up operator, L plus is step up operator, and this is a step down operator. Or both of them together, they are known as ladder operator. L plus minus, they are ladder operator. Ladder means stairs. पश्तो में अंदर पाया सीढ़ी, okay, ladder. Step and step down mean कि it steps up something and it steps down something. What it steps up and what it steps down, this we are going to see in a moment. Okay? I have just written that these are two operators. Now, when we started with the subject, I told you that one of the postulates rather tells you that the state of a system can be represented by psi r t. R is the position coordinate in 3 dimensions, t is the time coordinate. Now, if you ignore time, then this is just its space portion. Now, if you write it like this, it means it is in 1 dimension. And this thing can equivalent be written as psi x, y, z. These are several ways of writing wave functions. Okay? Now, since you can transform rectangular coordinates to spherical polar coordinates, and in spherical polar coordinates you have 3 variables r, theta, phi. In x, y, z coordinate you have x, y, z. So if you transform it, then your psi r, theta, phi is the same wave function in spherical polar coordinates, right? In spherical polar coordinate. And sometime we write them in the form of quantum numbers n, l, and m. Sometime we write them in the form of this n, l, and m. Now, n means principal quantum number, l means orbital angular momentum quantum number, and m means projection quantum number. Okay? So it is the principal quantum number, this is orbital angular momentum quantum number, and that is projection or magnetic quantum number. Now, question is, why we call it, well, principal quantum number, it is obvious when you are talking about hydrogen atom, then you say electron is in n is equal to 1. And when n is equal to 1, it means it is going there. So it means that it depends upon the radius r. When r varies, it means you are moving from one state to another state. Okay? So this r depends upon n. Then is orbital angular momentum quantum number, which depends upon not only r, but it depends upon theta as well, theta angle. And the last one it depends only on the projection. Okay, this thing I'll explain in detail in the live class next time. Okay, we'll start from here. Please remind me at that time. Okay, so my step will be to explain this quantum number, by what it represents, what it represents, what it represents. Okay, okay. I am going to finish it here today for today's thing. Come prepare with that thing, do all that mathematics. Physics is my job to explain it to you. You know, mathematics is the translation of physical concepts. Okay, and if you reconcile the two concepts together, you understand the subject. Okay, thank you very much. Bye. Se você puxa